Hey everyone, welcome back to physics. This will be lecture 24 of the course. And in this section, we're going to shift away from kind of our kinematics and Newton's laws of motion, and start looking at kind of a different way of thinking about motion. And specifically, we're going to kind of start with work and kinetic energy. So this lecture will kind of explore first of all, what are these things? And second, what is the connection between them? And it starts to get pretty interesting, as I think you'll agree. Let's go ahead and jump into it. We'll call this section 5.1, work and kinetic energy. Now, just to state from the onset, most of what is going to follow is kind of based on or stems from what's called the principle of the conservation of energy, And so I'm just going to state that kind of informally here. Principle of conservation of energy, right? And so this is something people will probably have heard of at least in passing. But the idea here is that energy is a quantity that can be converted from one form to another, but cannot be created or destroyed. So this is something that you may have heard of, and it really underpins a lot of this particular section's content. So let me just write it out here. Energy is a quantity that can be converted from one form to another, but cannot be created or destroyed. Okay, so that's kind of a basic statement of the conservation of energy. Now, this whole idea of energy being converted from one form to another, a really good example is like with the car. Right? A car, like a vehicle, like an automobile, chemical energy is stored in the fuel. Right? You push down on the gas pedal and the car moves. This chemical energy is then converted to motion. Right? And then once the car's in motion, hey, I want to slow the car down. You hit the brakes. And what happens? Well, that energy that's, present in the motion of the car is then converted to heat. Right? So you've got chemical energy that is converted to motion, which is then converted to heat. Right? And that's a great example of the idea of energy sort of being ever present, but being converted from one form to another. Okay, and so these are our concepts you're familiar with, at least you've heard of them. So what we want to talk about next is, so keeping in mind that this guy here kind of underlies a lot of what's to follow, we want to shift the discussion towards this idea of work. So what is work? So in everyday use, we've certainly used the word work all the time, right? Work. In everyday use, we call things like moving a heavy brick, or building a house, or learning a skill, or doing something. We call that work, right? So in everyday use, moving an object, sliding an object, and then things like more specifically like building houses, learning a skill. These are all examples of what you might call work in the everyday sense, right? And the idea behind each of these examples is that we have to expend energy to do work, right? We have to expend some sort of energy to do work. Now, in physics, the concept is similar, but as per usual, more precise. right? And so in physics, what we say is that the total work done on a particle by all of the forces that act on it equals the change in the particle's kinetic energy. Okay, so first of all, what is this kinetic energy? We'll define this really more specifically later. Kinetic energy is the energy of motion, we'll say, to start with. We'll define this more specifically later, more precisely. So the total work done to an object by all the forces that act on it equals the change in its kinetic energy. Okay. All right. So that's a great thing to say up front when we're talking about work. The total work done. If I do work on an object, I am effectively changing its kinetic energy. Okay. Now we'll see the connection between these things as we get further in, but we're just kind of building up some groundwork here, right? So what are some examples of work in the physics sense? So this is like the everyday sense up here, but in the physics sense, okay, what are some examples? Well, pulling a crate across a surface. Right, so I've got a, some kind of a crate, and I'm pulling it across the surface. So some distance, that crate is going to move across that distance. I would say that's an example of work. And we'll see in a second. We'll define work, but we're just kind of laying the groundwork here. Another example would be lifting a heavy brick off the ground. All right, so if I got some heavy brick and I lift it off the ground, I'm going to move it some distance. Okay, that's an example of work in the physics sense. Another example, pushing a car down the road. I mean, there's infinitely many examples. You can give lots of examples. The key thing about these examples is that in each of them, we do work by exerting a force on a body while the body moves. Right? So in each example, we do work by exerting a force which we'll denote as F in the usual sense, on a body. And then the key thing is while the body moves. From one place to another. And what does that really mean? Well, that's a displacement. And we'll denote that with an S. It's a vector, right? Okay. So in each of the examples, the key thing with work is some force being exerted on the body, and as a result, the body moving from one place to another. So there's displacement and force. Okay. And it turns out that, if you do, so the way to do more or less work is to make the force greater or smaller, or the displacement greater or smaller. So you do more work if, one, the force is greater. So it's you push harder, or you lift harder, or whatever, pull harder. Or if you push further, or pull further, or lift further. So force is greater, or displacement is greater. Right, and this should jive with your everyday notion of work, right? If I say to you, I need you to push this car 3 feet, a certain amount of work associated with that ask. If I say to you, I need you to push this car 50 feet, there's a certain amount of work associated with that ask. And obviously the latter is greater. Okay. And similarly, if I say I need you to push this tricycle 3 feet, there's a certain amount of force required to do that. If I say to you, I need you to push this cement truck 3 feet, a certain amount of force is going to be required to accomplish that. So that this is the way that work increases, is either through the force or the displacement. Okay, and so what is work then? Work, we denote with a W, is just equal to the force as a vector times the displacement. Okay, so that's sort of the way we think about work, right? And we'll get into some complexities of this definition, but just in general, think about it as force times displacement. Okay, so here force would be, in this context, a constant force, right, acting on a body, right? So we're not talking about variable forces yet. That'll be next section. But for now, we'll just assume the force is constant. A constant 200 newtons is applied, that kind of thing. And S is the displacement the body undergoes as a result of the force. So F, constant for now. And S is the displacement as a result of F. Okay. All right. And so clearly from this definition, you can see that the work is going to be greater if F is larger or if S is larger, right? So this fits the idea that we've laid out here. Okay, so this is work. Work is force over a displacement. Force times a displacement. Okay, now what is the units for work? Well, if work is equal to force times displacement, we know that force is equal to, newtons, and displacement is in meters. So this is what's called Newton meters. Another name for that is joules. Okay, so 1 Newton meter is 1 joule. We usually just denote it with a J. Right, so you're applying a certain amount of force over a certain distance, and that is called a joule. Okay. All right, very good. So this is all kind of wind up. We'll get into some of the more mathematical aspects here in a moment. Let's do a simple example just to make sure it's tracking. If I exert 10 newtons of force to push a car a distance of 20 meters, then I have exerted how much work? Then I have done how much work? Well, work is equal to the force times the displacement, right? In this case, everything's aligned. We'll get into how this can become weird in the next example, but basically you want to think of this as just the magnitudes multiplied together in this example. All right, so 10 newtons times the distance of 20 meters. So I've done 200 Newton meters or 200 joules of work. Okay. Right, so that's the idea. If you've got the force, it's exerted over a certain distance, then that's the work is a simple product. Okay. Now, how can this become a little more complex, right? Well, it's important to note that the force, all of the force that I exert may not be counted as work, right? So not all of F may be counted as work. What do I mean by that? Well, in order for force to be a factor in the work equation here, it has to be in the direction of the displacement. So F must be in the direction of S. to be part of the work. Okay, and a nice simple example of that would be, well, a simple example would be like, think of a car, right? So I've got some kind of a car here, and I'm pushing it, like, the previous example for, right? So I've got a car, and I'm behind the car, and I'm pushing it. Okay, so maybe I'm pushing it at a bit of an angle, like an upward angle, and maybe the force is kind of directed like this, right? So this is the force, the direction of the push. It's kind of upward. Well, only a portion of the force that is being applied to the car is actually in the direction of the displacement. So the car is on a road, right? And so its displacement is along that road. It's a vector along that road, right? So you can think of this force vector as having, kind of an x component, and, maybe there's a y axis here, and it's also going to have a y component. Okay, and there's some angle here between the displacement vector s and the force vector f. So really only this part here contributes to work. Right, we know this vertical component of the force is kind of wasted in terms of work. Now, if I want all of the force to contribute to the work, then I'm going to have to just level out my force vector, right? And then it's all in the direction of the displacement. But if I was just casually pushing on this car, maybe I have an upward, force vector, then only a portion of that force vector is actually contributing to the work. Okay? Okay, and so if you think about this triangle here, you've got your theta, you've got your F, and we'll say that the displacement is in the direction of this lower leg here, then this is the part that's contributing to the work, and so we would say that the cosine of theta is equal to, what, x over F, which means that x is equal to the force times cosine of theta. So that's the part that goes into work, right? So technically, work, which we just had said is F times S, is actually F cosine of theta times S, right? Which will frequently, kind of change the order, and we'll just write Fs cos theta. Okay. All right, so technically this is the work, right? If your force vector isn't perfectly aligned with your displacement vector, then you're going to have to scale it using this cosine factor. All right. And so if you look closely at this, and if you've done some linear algebra or you've seen some vector stuff, this might jump out at you as being basically an expression for something you more familiar, more basic, and that is the scalar product, right? So F S cos theta has the form of a scalar product. Right, so let's remember what that is. So that's also known as the dot product. A dot B. A is a vector, B is a vector. You dot them. Well, you can see that that's the magnitude of A, which is a scalar, times the magnitude of B, which is a scalar, times cosine of theta, where what's theta? Theta is the angle between A and B. Right, so that's the dot product. This is also known as the dot product. Right, and so you might remember that A dot B, well, if your vector A is, like AX, like a two-dimensional vector, it might be AX, AY, and then your B vector might be BX, BY. Then A dot B is just AX, BX plus AY, BY, this regular multiplication. Okay, and so frequently when we write W equals Fs, we'll frequently use the notation F dot S to mean that this is the dot product. This is the scalar product of the force vector and the displacement vector. And if we think of it as the dot product, then that naturally is going to take into account that we're only interested in counting the component of force that's aligned with the motion, the actual displacement, as work. Okay, and so this is usually what we'll define as work, F dot S, meaning the scalar product. Okay, now let's do an example to kind of make all this a little more tangible, because I realize this is a lot of running around, but let's do an example. Let me write this example out. This is a great example. It's a great example. You exert a force of 210 newtons on a crate. Newtons on a crate. Okay. The crate, it has some nails on it, right? So, so top down, it's a crate and you're pushing on it. Maybe one side is a little like scuffed up. And so it's got this tendency to kind of deviate. It's not, like this side is going to drag heavier than this side. So if you just push straight on it, it's going to kind of follow a winding path. And that's maybe because there's some exposed nails or the surface is rougher underneath it or something. So the crate has a tendency to slide easier on one side than on the other. So we'll just say the crate doesn't slide evenly. Okay. The crate doesn't slide evenly. All right, maybe it's rougher on one side. Hopefully you can imagine this scenario, right? And so to get the crate to slide in the intended direction, you have to exert a force 30 degrees off the displacement path. So to get the crate to slide straight, whatever that means, I'll just put straight, so you've got some idea you want it to go like that, but if you just push directly on it, it's gonna go crooked. So to get the crate to slide straight, you have to exert a force 30 degrees off the displacement path. I'll just say the intended path. Displacement path. All right, so if you push the crate for 18 meters, how much work have you done? Okay, how much work have you done? All right, so top-down view. Okay, you've got the crate here. I exert a force on it. Okay, and that force is 210 newtons. Now I want the crate to move in this direction, right? And so I've determined ahead of time that in order to do that, given the stickiness of one side of the crate and its tendency to drag on one side, I have to angle my force vector approximately 30 degrees. So I have to push 30 degrees off of the path I want it to go in order for it to go down that path. Okay. And so the question is, what is the work done if the displacement that I'm after is 18 meters? Okay, I'm gonna apply this force until the crate has moved through 18 meters of displacement along this path, this S path. Okay, so what is the work? Well, the work is F dot S, right? Which we know this is the dot product, scalar product. So there's two different ways to represent it. You could think of it as the dot product if you're thinking of these as vectors, but if you're thinking of these as just magnitudes or quantities, you can also do something like this. The magnitude of F times the magnitude of S times the cosine of the angle between them. Okay, and so since we're kind of given this information, this is the more straightforward approach in this example. So I would say it's 210 newtons. That's the magnitude of the force vector. And the magnitude of the displacement is, well, it's just 18 meters. and the cosine of 30 degrees. Okay, so when you crunch all those numbers, you will get something like 3,273 joules. Newton meters, right? Otherwise known as joules. All right, so this would be sort of the straightforward approach to calculating this. Now the idea here, what I've done is I've said, okay, there's an x component of this force vector. There's also a y component of this force vector. I've effectively removed this part from the calculation, right? So when I take f cos 30, I'm specifically scaling this 210 to just this piece. Now you can also solve this problem using vectors, right? And I think it's instructive to just kind of see what that looks like, right? You can also use vectors to solve this. So let me write that. You can also use vectors to solve this. Okay, so let's say I've got this triangle, 30 degrees here. Here I've got my force. Here's x and here's y. And the direction of the displacement is along this x direction. Well, cos 30 degrees is x over 210 newtons, which means that x is equal to 210 newtons times cosine of 30 degrees, which means my x component of the force is equal to 182 newtons. Sine of 30 degrees is y over 210 newtons. So my y component of force is 210 newtons times the sine of 30 degrees, which is 105 newtons. And take a moment to make sure that calculation makes sense to you. All right, but I'm just saying, okay, I've got the force vector. What's my x and y component? Just using like this basic trig, right? Okay, and so that means my force vector can be written as 182 newtons, comma 105 newtons. If you like this notation, if you're an engineer and you prefer IJ notation, you could write it like this: 182 newtons I hat plus 105 newtons J hat. That's my force vector. What's my displacement vector? Well, the way we've coordinatized the problem, it's just moving in this direction, the x direction. There is no y component, right? So my s vector would be 18 meters, comma 0 meters, or if you prefer, 18 meters I hat plus 0 meters J hat. Okay, and so work is just equal to F dot S, right? And so that's 182 newtons, 105 newtons, dot 18 meters, comma 0 meters. And I know that's 182 newtons times 18 meters plus 105 newtons times 0 meters. Of course, that's all 0. And so this is the calculation, and we get 3273 newton meters joules. Okay, so you see how the calculation kind of works either direction. Now, in this example, I mean, given the way it's set up, this is clearly more straightforward. You know, you're told the magnitude, you're told the angle. It's very straightforward to just plug it into this expression. But just know that anytime you can do that, you can also do this. You can calculate the actual vectors. And in some cases, this will be preferable. Okay, in some cases, this will be preferable. But you see, you get the same answer. It's really the same calculation, isn't it? Okay, very good. Now, let's talk a little bit more about work as a quantity. Now, in this previous example, we saw that work was positive. And in the example preceding this one, we also saw that it was a positive quantity. But it turns out that work as a quantity can be negative or 0 also. It is possible to do negative work, and it is also possible to do 0 work, even if a force is exerted, right? So how does this all work out? Well, we'll start by positive force. So, sorry, positive work. So when force, the way it breaks down is that when force has a component in the same direction as displacement, then you get work greater than 0. So the idea is I've got a particle and it's being displaced along a path. Now my force vector could be perfectly aligned with that displacement. It could be a little bit off, right? But so long as one of the components is in the direction of the displacement, then the work will be positive. So you can see here this component, so the force vector would have these two components, right? So it's this direction and that direction. One of them is in the direction of S. Okay, and so as long as that's the case, then you've got positive work. So what about negative work? When force has a component in the opposite direction as S, then the work is negative. Okay, so a negative work. Now what might that look like? Well, same scenario. I've got an object moving in this direction. It's undergoing displacement, but I've got a force maybe over here. Right, so in this case, what are the components of F? Well, it would look like this, and it would look like this, right? Right, so notice this guy here is opposite. Right, now this one up here, there's no way to, this force vector doesn't have a component opposite S, right? There's no part of this force vector that's pushing in the direction opposite of S, right? There's a part of it that's pushing in the direction of S, and there's a part of it that's pushing other, or perpendicular to S in this case, right? But there's no part of it that's pushing opposite. Now down here, you've got a part that's pushing opposite the direction of S and a part that's pushing perpendicular, right? That's all. So if the force vector isn't perfectly aligned with displacement, some part of it is going to be perpendicular, right? Some part of it's going to be in line, right? And it's either going to be in the direction or the opposite direction. Okay, and so you can see the difference there. And then of course, when is work going to be equal to 0? Well, when the force is perpendicular to displacement, then work is equal to 0. And so that's this obvious case where I've got some displacement and I'm applying a force that's perpendicular, meaning a right angle with that displacement. So that would be like a crate sliding along the floor. So this is side view. The crate sliding along the floor, right? So you got displacement in this direction, but maybe I'm pushing down on it. Well, in this case, no component of that force is in the direction of the displacement. And so if you did a dot product there, you know, the force you'd get 0, right? So you would get 0. Okay. And the cosine, and this would be like either cosine of 90 degrees or cosine of 270 degrees, and those are both 0 also. Right, so even if you tried to use just the trig, you would see that this generates a 0 for the work. Okay, and so a nice way to think about this is to think about like what a weightlifter does. So if you imagine weights, like a weight set. Okay, so I've got some like barbell. The weight maybe starts on the ground. We'll say this is touching the ground here. Okay. So the weight starts on the ground and a force is applied, upward force. Okay, so an upward force is applied and the bar goes up. So displacement and force would be in the same direction. So weight starts on the ground, F is up, S is up, right? Presume if I pull up hard enough on the weight, it's going to go up. It's going to lift off the ground. And so in this case, the work being done by the weight lifter is greater than 0. Now, once the bar's in motion and being displaced upward, the force is going to be slackened, right? So if you're lifting a weight and you want to stop the weight from going up, you sort of ease back on your force. But nonetheless, because this thing is heavy, your force is still upward, right? So once the bar is in the air, all right, we'll kind of curve it. The force is still up, but it's less, right? You maybe ease back. You're not pulling quite so hard. But at a certain point, when you slacken your force, the barbell is going to slow down, and eventually the displacement is going to be equal to 0. This thing will stop moving up. Okay. So here we would say the force is slackened, and the bar reaches the top of its trajectory. Right? And at that point, it stops. Right? So at that very point, at the top of the trajectory, when the bar is no longer moving up, but I'm still exerting a force, then the work is equal to 0. I'm still exerting a force, but the bar just isn't moving. Okay? So then what happens? What's next? Well, then the bar starts to move down. So I've got my weights, and I lessen my, perhaps I lessen my force a little bit more, and suddenly the weights start to descend. Right? So this thing is gonna, so first it starts off the ground, it goes up, and then it stops, and then it starts to go down. Right? All three instances, my force is still always upward. It's varying, but it's upward, right? The displacement is initially going to go up, and then it's going to stop, and then it's going to go down. So here, force is slackened, and the bar starts to descend. Right? It's heading down. And so what's my work look like there? Well, my force is opposite the displacement, and so my work is negative. Okay, so work is just in the motion of lifting a bar and then setting it down. The work starts out positive, it becomes 0, and then it goes negative. Does that make sense? Hopefully that makes sense. It's a nice example of how this work is kind of fluid, and it sort of depends on the displacement and the force and the direction of those two things. Okay, very good. Very good. All right. Perfect. Let's take a look at another example. Okay, a little more complicated scenario, and let's see if we can calculate all of the necessary work objects. So here's the example. A farmer pulls a trailer 20 meters along level ground. The trailer weighs 14,700 newtons. The tractor exerts 5,000 newtons at an angle of 36.9 degrees above horizontal. Okay. And let's throw some friction in here just to make it more interesting. There is a 3,500 Newton friction force opposing the displacement. Okay, so there we go. So what does this look like? Well, okay, well, what are we interested in? We want to find the work done by each force and the total work. Find the work done by each force and the total work. Okay, so what does this look like? This is a side view. So I've got a tractor and hold on a sec. Yeah, okay. So I got a tractor pulling a trailer 20 meters. So I've got a displacement, we'll say in this direction, and that's going to be 20 meters. Okay. So the weight of the, and think of this as just kind of an add-on to the free body diagram. So what's the weight of the tractor? Well, it's given. It's 14,700 newtons. And then, of course, there's a normal force opposing that because the tractor's not accelerating. Okay. And then there's a force being applied by the tractor. It's off the horizontal, right? So assume the tractor's moving along the horizontal here. So that force is 5,000 newtons, right? And we're told that it's 36.9 degrees off the horizontal. Okay. All right. And then we also have friction, which I'll just write like that. And the friction is, we're told, is 3,500 newtons. So all these quantities are nicely given to us in this example. Okay, let's calculate the work done by each of these forces. So you've got the force of the tractor. I'm going to put a T under there. You've got the weight, right? And you've got the friction and the normal force, right? So there's 4 forces at work on this trailer, and let's figure out what the work is in each case. So the work done by the tractor, denote it like this. Well, it's going to be the force done by the tractor dotted against the displacement, right? And so we're given the angle, we're given the magnitudes. Let's just use Fs cos theta, right? So the force of the tractor, magnitude, times the magnitude of the displacement, times the cosine of theta, right? And so in this case, that is what? 5,000 newtons. That's the force done by the tractor, the magnitude over 20 meters, and the cosine of 36.9 degrees. So all that information just be read right off here. And so when we calculate all of that, we see the work being done by the tractor is approximately 79,968 joules. So that's the work done by the tractor, approximately 80,000 joules. 80,000 newton meters. What about friction? What about the work done by friction? Well, same calculation, right? It's the magnitude of the force of friction times the magnitude of the displacement times the cosine of the angle between those two. And so what is that in this case? Well, you got 3,500 newtons times 20 meters. Now what's the angle between the displacement and the friction vector, right? Remember, that's this whole thing. So it's 180 degrees, isn't it? Cosine of 180 degrees. And what do we get there? Well, the key thing that I want to point out here is this piece. So I'm going to rewrite this so I can actually explicitly write this. Cosine of 180 degrees is -1. Right? And so this is what makes the work negative in this case, right? The friction force is entirely opposite of the displacement vector, okay? And so all of that force is negative, okay? And so what you get here is about negative 70,000 joules. I think it's exactly that. Okay, so that friction force almost entirely the work done by friction almost entirely offsets the work done by the tractor, which is interesting. But you can see they're comparable forces, 5,000 newtons, 3,500 newtons. This one is entirely opposite, right? So all of it is going into that. Here it's a little off, right? So it's not quite all of it, only really this piece of it here. This piece is being completely ignored as part of in the work calculation. If that tractor were to level this out, this would be much much different, right? But okay, anyways, so that's the work done by friction. What about the work done by the weight of the tractor? Okay, so I'm just going to denote that WW here. So that is just the magnitude of the weight vector times the magnitude of the displacement times the cosine of the angle between them. And so we get what? 14,700 newtons. That's the weight times 20 meters again. And then the cosine here is cosine of 270 degrees, right? So that is 0, right? So you get 0 joules. All right, remember your trigonometry here. If we go all the way around to here, right? That's what we see in the diagram. That's 270 degrees between those two, or you could use negative 90 degrees. That would be fine too. Either way, you're going to get 0 as your cosine of the angle. Right, so you get 0 joules for the work being done by the weight. And then, of course, you're going to get the same thing for the normal force, right? Right, so I won't even enter it, but you also get 0 joules, right? For the same reason, right? This is a 90-degree angle. Cosine of 90 degrees is 0. And you can just see that the normal force is perpendicular to the displacement, as is the weight. They're both perpendicular. Those forces are being applied perpendicular to the displacement of the tractor, and so the work is 0. Perfect. Okay. And so then, so this kind of answers the first part. What's the work done by each force? And then the second question is, what is the total work done, right, by all of the forces? Well, the work in total is just equal to the sum of all of the works we just calculated. So it's equal to the work done by the tractor plus the work done by friction plus the work done by the weight plus the work done by the normal force. And in this case, that's 79,968 joules plus negative 70,000 joules plus 0 joules plus 0 joules. And so I get 9,968 joules done worth of work. Okay. So that is the total work done on the trailer by all of the forces involved. Okay. All right, very good. So that's the idea of work. Work is force being applied to an object in the direction of displacement. Okay. And so what we want to do next is we want to transition to a discussion about kinetic energy. So how does kinetic energy relate to work? And so I think, given the length of this section, I'm going to split the lecture into 2 parts, so part A and part B. So this will conclude part A, and we'll next transition the idea of work to kinetic energy in part B. So stay tuned for that.